Hi, my name is Chandrashekar S. I'm giving a seminar EOS and TNEOS. First of all, EOS, Embedded Configurable OS, is a open source, royalty free, and real-time operating system intended for embedded applications. The system is targeted at a high performance small embedded systems. For such systems, an embedded form of Linux or other commercial OS not provided the streamlined software required. This is the ECAS configuration tool. The top level of ECAS configuration is seen as by the tool user. For each item in the list, left-handed window can be selected or deselected. This figure shows the ECAS configuration tool for kernel details. This figure shows the loading and ECAS configuration. This is a typical example of overall process of creating binary image to execute an embedded system. This process is run on source system, example Windows or Linux platform, and executable image is destined to execute on a target embedded system such as a sensor in an industrial environment. At the highest software level is the application source code for particular embedded systems. This code is independent of ECAS but makes use of application programming interface to sit on top of ECAS software. There may be only one version of application source code, or there may be variation for different versions of the target embedded platform. In this example, GNU utility is used to selectively determine which pieces of program need to be compiled or recompiled. Hey. ECAS layered structure. A key design requirement for ECAS is portably different architecture and platform which is minimal effort. To meet this requirement, ECAS consists of a layered set of components. These are the layered structure: user application code, standard C library, IO systems, kernel and hardware abstract layer. Hardware abstract layer. Hardware abstract layer consists of APIs to upper layer, and each hardware platform is different. Let's see the code. This is the HAL for ARM architecture and PowerPC architecture. The two implementation HAL enables interrupts and macros. These are the HAL modules: architecture, variant and platform. HAL is implemented at three separate modules architectures. The architecture defines the process family type. This module contains code necessary for processor setup, interrupt delivery, context switching and other functionality to specific instruction set of architecture that process family. Second one is variant. This supports features of specific processor in the family. An example of supported feature in an on-chip module such as memory management unit (MMU). Third one is platform. They extended the HAL support to tightly coupled peripherals like interrupt controller and timer devices. This module defines the platform or board that includes the selected processor architecture and variant. It includes code for startup, chip selection, configuration, interrupt controller and timer devices. The next one is ECAS kernel design. The ECAS kernel was designed to satisfy your main objectives like low interrupt latency, the time it takes to respond to an interrupt and begin executing an ISR. And next one is low task switching latency, the time it takes from when a thread becomes available to when actual execution begins. A third one is small memory footprint. The memory resources for both program and data are kept into a minimum by all components to configure memory as needed. The last and fourth one is deterministic behavior. Throughout all aspects of execution, the kernel performance must be predictable and bounded to meet real-time applications environment. The next one is what is not there in ECAS kernel. Some functionalities that typically included in the kernel of OS but not included in the ECAS kernel. Example, memory allocation is handled by a separate package. Similarly, each device driver is separated package. ECAS IO system. ECAS input-output system is a framework for supporting device drivers. A variety of drivers for a variety of platforms are provided in the ECAS configuration package. These include drivers for serial devices, Ethernet, flash memory, interfaces and various IO interconnects such as PCI, Peripheral Component Interconnect, and USB, Universal Serial Bus. In addition to user can develop their own device drivers. Principal objective for input-output system is efficiency with no unnecessary software layering or extraneous functionality. The device drivers provides necessary functions for input, output, buffering and device control. Device drivers and other higher layer software may be implemented directly on HAL if this is appropriate. If specialized kernel type function are needed, then the device drivers is implemented and using kernel APIs. ECAS scheduler. The ECAS kernel can be configured to provide one of the two scheduler designs, bitmap scheduler and another one is multi-level queue scheduler. In first, bitmap scheduler provides efficient scheduling for a system with a small number of threads that may be active at point in the time. Multi-queue scheduler is appropriate if the number of threads is dynamic or if it is desirable to have multiple threads at same priority level. The multi-level scheduler is also needed if time slicing is desired. Bitmap scheduler priority levels. A bitmap scheduler supports multiple priority levels, but only one thread can exist at each priority level at a given time. Scheduling decisions are quite simple with this scheduler. When a block thread becomes ready to run, it may preempt a thread of lower priority. When a running thread suspends, the ready thread with the highest priority is dispatched. A thread can be suspended because it blocked on a synchronization preemptive, because it is interrupted, or because it is relinquish control. Because there are only one thread at most, each priority level scheduler does not have to make a decision as to which thread at a given priority level should be dispatched next. The bitmap scheduler is configured with 8, 16 or 32 priority levels. A simple bitmap is kept of the thread that are ready to execute. Scheduler need only determine the position of the most significant bit to make scheduling decisions. This is the multi-level queue scheduler priorities. This figure shows the ECAS scheduler options. The multi-level scheduler supports up to 32 priority levels. The multi-level queue scheduler allows for multiple active threads at each priority level, limited only by system resources. This figure illustrates the nature of multi-level queue scheduler. A data structure represents the number of ready threads. This is here, thread C is ready. When a thread block becomes ready to run, it may preempt a thread of lower priority. As with the bitmap scheduler, a running thread may be blocked on synchronization preemptive because it is interrupted or because it relinquishes control. ECAS thread synchronization. The ECAS kernel can be configured to include one or more of 6 different thread synchronization mechanisms. These include classic synchronization mechanisms, mutex, semaphore, and condition variables. In addition to ECAS support two synchronizations or communication mechanisms that are common in real time, namely event flags and mailboxes. Finally, the ECAS kernel supports spin locks, which are useful in symmetric multiprocessing systems. This is mutex enforces mutually exclusive access to a resource, allowing only one thread at a time to gain access. The mutex has only two states, locked and unlocked. Similar to a binary semaphore, when a mutex is locked by one thread, any other thread attempting to lock the mutex is blocked. When the mutex is unlocked, then one of the threads blocked on this mutex is unblocked and allowed only to lock the mutex and gain access to the resource. Mutex differs from a binary semaphore in two respects. The thread that locks the mutex must be one to unlock it, but it is responsible for one thread to lock a binary semaphore and for another to unlock it. But it is possible for one thread to lock a binary semaphore and another to unlock it. The other difference is that a mutex provides protection against priority inversion, whereas a simple semaphore does not it. ECAS kernel can be configured to support either a priority inheritance protocol or priority ceiling protocol. These are mutexes and condition variables. The condition variable is used to block a thread until a particular condition becomes true. A condition variable are used with mutex to allow multiple thread access to shared data. In ECAS, condition variables are typically used in conjunction with mutex to implement long-term waits for some conditions to become true. This is the mutex and condition variables used in the ECAS operating system. Next one is TinyOS. The TinyOS takes the process of streaming a too much further point, resulting in a very minimal OS for embedded systems. The core OS requires 40 bytes of code and data memory combined. The TinyOS represents a significant departure from other embedded operating systems. TinyOS is not a real-time operating system. The reason for this is expected overload, which is in the context of wireless sensor networks. Because of power consumptions, these devices are off most of the time. Applications tends to be simple with processor convention, not much of an issue. In TinyOS, there is no kernel, there is no memory protection, and it is a component-based operating system. In TinyOS, there are no processors. The OS itself does not have a memory allocation system. Interrupt and execution handling is dependent on the peripherals. It is completely unblocking, so there are few explicit synchronization primitives. This is the wireless sensor network topology. The dark line shows the wired link and dotted gives the wireless link. TinyOS was developed primarily for use with network of small wireless sensors. A number of trends have enabled the development of extremely compact low power sensors. The low cost, low size, low power consumption wireless sensors can be used in a host of applications. This figure shows the typical configuration of wireless sensor network topology. The main goals of an TinyOS is With the TinyOS distributed sensor applications in mind, the following goals were set for TinyOS. Allows high concurrency. In a typical wireless sensor network applications, the devices are concurrency intensive. Several different flows of data must be kept moving simultaneously. And third one is while sensor data is input in a steady stream, the processed result must be transmitted in a steady stream. Also, external control from remote sensors or base stations must be managed. Operate with limited resources. Target platform has limited memory and computational resources and run on batteries or solar powers. Single platform may offer only kilobits of program memory and hundreds of bytes of RAM. The software must take efficient use of available process and memory resources while enabling low process communications. Adapt to hardware evolutions. Hardware is in constant evolution. Applications and most system services must be portable across hardware generation. It should be possible to upgrade the hardware with little or no software change if the functionality is the same. The fourth one is software. It supports a wide range of applications. Applications exhibit a wide range of requirements in terms of lifetime, combinations of communication, sensing, and so on. Fifth one is supports diverse set of platforms. A general purpose embedded operating system is desirable and it must be robust. Once deployed, a sensor network must be run unattended for months or years. Ideally, there should be redundancy both within a single system and across the network of sensors. However, both types of redundancy requires additional resources. One software characteristic that can be improved robustness is to use highly modular standard software components. These are the TinyOS components. Embedded software systems built with TinyOS consist of the set of modules called components such as single hop networking, ad hoc routing, power management, times, non-volatile storage. Next one is timer M component. The all component in TinyOS configuration have the same structure as an example shown in here. The standard box in the diagram indicates the components which is treated as an object that can only be accessed by defined interface indicated by white boxes. The component may be hardware or softwares. This is the timer M configuration. Components are organized into configurations by writing together at their interfaces and equating the interfaces of configuration with some of the interfaces of the component. A simple example as shown in the figure. The next one is TinyOS schedulers. The TinyOS schedulers operates across all the components. Virtually all embedded systems using TinyOS will be uniprocessor systems, so that only one task among all the tasks in all the components may be executed at a time. Scheduler is a separate component. It is one portion of TinyOS that must be present in any system. The default scheduler in TinyOS is a simple first in first out queue. A task is posted to a scheduler either as a result of an event which triggers the position or as a result of specific request by running task to a scheduler to another task. Scheduler is a power aware. This means that the scheduler puts processor to sleep when there are no tasks in the queue. The peripherals remain operating so that one of them can wake up the system by means of hardware event. signal to a lowest level component. Once the queue is empty, another task can be scheduled only as a result of direct hardware event. This behavior enables efficient battery usage. This figure shows the configuration assembled from software and hardware components. This simplified example called SURG perform periodic TinyOS applications. This figure shows the portion of configuration for the surge applications. The TinyOS resource interfaces. The TinyOS provides a simple but powerful set of conventions for dealing with resources. First one is dedicated, a resource that a subsystem need exclusive access to at all times. In this class of resources, no sharing policy is needed since only a single component ever requires use of resources. Example of dedicated abstraction includes interrupts and counters. The second one is virtualized. Every client of a virtualized resource interacts with it as if begin multiplexed on top of a single underlying resources. The virtual abstraction may be used when the underlying resources need not be protected by mutual exclusion. An, an example for this virtualized is a clock or timer. A third one is shared. The TinyOS resource information abstraction provides access to a dedicated resource through an arbiter components. Arbiter enforces mutual exclusion, allowing only one user are called client at time to have access to a resource by enabling the system to lock the resources. This figure shows the shared resource configuration. This figure shows a simplified view of shared resource configuration used to provide access to any underlying resources. Associated with each resource to be shared is an arbiter component. The arbiter enforces a policy that enables a client to lock resources and then releases the resources. Thank you.